Representative from International Peace Foundation, Deans of the Faculty of Science, academic colleague, distinguished guests, ladies and gentlemen, of Nobel Laureate Science Lecture. We are very proud and privileged to hold the world's most distinguished scientists. Professor David Cross from the Institute of Theoretical Physics, University of California, was the Nobel Prize Laureate for Physics in the year 2004. And we are certainly true in the case of Professor Cross' work, and his lecture today should serve us as an inspiration.
Bridges is facilitated by the International Peace Foundation, an unpolitical and unreligious foundation under the common patronage of 21 Nobel Peace Prize laureates based in Vienna. The event by finding ways of working together. After the success of bridges in Thailand, the Philippines and Malaysia, the International Peace Foundation has now been invited by other ASEAN countries to build further bridges towards peace and international understanding by expanding its program in Southeast Asia to stimulate the intellectual, scientific, and cultural exchange in the region. The topics of the ongoing events deal with the overall theme of building a culture of peace and development in a globalized world. And with
Happy New Year. Everybody see this. It is beautiful Monday in Chiang Mai. And today I have great pleasure in introducing to you one of the most admired.
physics, you don't have to be scared. But for those of you who are in physics, I hope that after the lecture, you'll have time to ask me about string theory or quantum computing or whatever you want, including life in Berkeley in the 60s. So, is this working now? So, my talk is on science. What it has brought us, what it will bring us, and some general speculation about science and what we will learn, and about the human condition in general. Mostly I'm going to talk about, in a very general sense, the gifts of science. What science has brought us. And the first of the gifts that I will discuss is just the scientific method alone. For even without the fruits of knowledge that science brings us and their application to technology, the greatest gift that science brings us is a new way of thinking. And this new way of thinking, which the scientific method is of course extremely powerful in science, but it's a powerful and important way of thinking that could be as useful and is as useful in all areas of human study and all areas of human discourse. Then I'll briefly discuss the knowledge of nature that science provides. This is its most obvious gift, understanding how nature works. And I'll give some examples from both physics, astronomy, biology, which have totally changed our understanding of nature in a very short time. We apply that knowledge that we have gained to control nature, to try to manipulate and use nature to our advantage. So the third topic will be the control of nature, application of science, technology, which has brought us so many good things and so many bad things. And in responding to those bad things, to the problems we face, some of which are consequences of our ability to even change the face of our planet, international character. And I'll speculate on how that might serve as a model for a growing internationalism that we truly need to solve some of the planet's problems. And as a scientist, I will end with questions, because that is the driving force of science. And as a theoretical physicist, of course, my business is to make predictions. So I'll make some predictions. Whereas we humans have been talking for maybe 100,000 years or more. And it's proved to be very powerful, and it's based primarily on the idea that the only authority for truth in the end is agreement with nature through observation and experiment, and not on the basis of power or religious faith and dogma. So the first time I met the Dalai Lama, who I've met a few times, we had a very interesting discussion about science and religion. And I asked him, is there anything that science is currently exploring, any answer that we might find that would be in conflict, would cause you problems with Buddhism as you practice it, which they understand and is tested on the basis of observation and experiment, and our writings say otherwise, we must agree with science. I was very impressed by the Dalai Lama. And scientists know also that their truths, what they learn, their theories that are tested, are not going to last forever. They are always provisional. They're very likely to be changed. And we continue to subject our theories to quantitative tests and improvement. We look for nature to tell us that our theories are wrong. Then we've learned something very important, and we try to construct a better theory. Has been replaced by quantum mechanics and by relativistic mechanics, but it is still an extremely good approximation to the better theories. Theories in physics don't die, they just become approximations. Anything that stops discussion, stifles debate, promotes authority, is bad for science. Science promotes tolerance. We might be wrong. Any idea I have might be wrong. Because we all, as scientists, we all understand that everyone is equal in science. I can give a lecture describing my theory, and a bright young student with no credentials can get up and say, "But you're wrong." And he might be right, only because they're good for science, but they're also good for tolerance, for democracy, for openness, transparency. But of course, the main goal of science is to provide knowledge of nature. We human beings are programmed biologically for our survival to construct models, explanations of the world. 400 years is not a long time. That's the life of 6 people, one after another. So just 6 lifetimes ago, Galileo and Newton started the scientific approach to physics. And now we have a theory that seems to explain just about everything until we get down to very, very short distances. Astrophysics, people have been doing forever. Astronomy, looking at the stars, trying to understand what the universe is made of. In the last 100 years, we have gone from thinking that we lived in a static Milky Way and that was the universe, to understanding the whole history of the universe from almost its beginning. So let's start with physics. And I've tried to summarize in a few sentences what we've learned over 400 years. At the beginning, Galileo and Newton discovered the basic laws of motion that govern motion of bodies, and the symmetries of nature that we've learned more and more are the basis of that dictate the forces that act on bodies and make them move. We have unveiled the structure of matter, the underlying atomic structure of matter, constituents of all the matter we see naturally around us. And in the last 100 years, we have constructed a basic constituents of matter, and now we are engaged in an ambitious attempt, who, aside from being a great experimentalist and developing the telescope and other experimental tools, was also a theoretical physicist. And he understood the first time that the language of science is mathematics, which is why it's often so hard to explain physics to people who don't know mathematics. Mathematics, our most highly developed form of language, is necessary to understand nature. And the more we learn about nature at its most fundamental level, the more we discover a beautiful mathematical structure behind. Used Galileo's insights and the mathematics he developed and his intuition to construct a universal theory for the first time that both explained apples and planets, subject to the same law of gravity, and a theory strong and powerful enough that he could predict and calculate with precision the motion of the planets. And Newton's theory was so powerful that it set the stage for all of modern science. This goal of constructing a quantitative explanation of all phenomena continually subjected to experimental test. And this was all done just in the first 100 years. In the 19th century, Maxwell unified the phenomena of magnetism and electricity and realized that light was a wave in the electromagnetic field that described electricity. And all of the phenomena of light and electricity and magnetism could be summarized in a set of beautiful equations that you could put on one t-shirt. This was also the century of the Industrial Revolution, where we learned to construct machines and transform heat into mechanical work. We understood heat and energy and entropy. And this is one of the heroes of that development, Ludwig Boltzmann, who understood what entropy was really about. And finally, in the 20th century, we completed the atomic theory of matter, starting with the realization that all ordinary matter is made of atoms. Atoms have a structure. They're not just little hard dots. They have a structure. They consist of a very small nucleus and an electron cloud whirling around that determines the structure of individual atoms and molecules. So atoms, we understood, are electrons revolving around nuclei, and in order to understand their structure, one had to invent quantum mechanics, a whole new way of looking at the world, replacing classical mechanics. Here are some of the heroes that did this great development in the beginning of the 20th century: Planck and Einstein, Schrödinger, Bohr, Heisenberg and Dirac, and of course Rutherford, who discovered the nucleus. And as it has turned out, over the century and continuing today, we understand that the collective behavior of atoms is responsible for all the properties and phases and behavior of matter, including all of chemistry. And supposedly all of biology is determined by just these atoms interacting with each other. The basic equations that describe this could also be written on one t-shirt. That's not to say we understand how biochemistry and biology work based on that t-shirt, but in principle, we think that is the case. Also in the 20th century, we learned that space-time is more complicated than we thought. It's dynamical, said Einstein, and mass and energy curve space, giving rise to gravity. And finally, in the last half of the 20th century, my generation, we completed the so-called standard model, or the standard theory of particles. We identified all of the elementary particles of nature that constitute ordinary matter, and they consist of quarks inside the nucleus, electrons, a cloud around the nucleus, accompanied by neutrinos, very light particles. We discovered 3 families of such particles, and most importantly, we identified the 3 basic forces of nature in addition to gravity. Force of electromagnetism was known for quite a while, but in the 20th century we understood the force that acts inside the nucleus, the strong and weak nuclear forces. And I'll say a word about the strong nuclear force because that's the one that we figured out. So, the nuclear force. This was a very hard force to understand since it operated inside this teeny little nucleus that is buried inside the atom and hard to peer within. And as we began to look inside the nucleus, experiments showed, just as I was leaving graduate school, that the proton looked as if it were made out of freely moving point-like particles called quarks. Very strange particles with fractional electric charge that no one had ever seen. But it looked, you could explain the experiments that scattered electrons off these protons if they were made out of quarks moving freely inside the proton. But that made no sense at all, because you couldn't pull the quarks out of the proton. You hit the protons hard, the quarks never came out. But if they were moving freely, what's stopping them from coming out? And that eventually led us to discovering a new phenomena, which led us to the theory behind this strange behavior, and turned out to be the theory of the nuclear force. And I'll spend a bit on the physics here because it's interesting. It all depends on the properties of the vacuum. Now, the vacuum, you might think, is pretty boring. And that's true in the classical world. The classical vacuum is empty. You know, if you take everything out of this room, all the people and the air and the rug, the furniture, and you're left with nothing, that's the vacuum, right? Boring. This is a picture of the classical vacuum. Or here's a better picture of the classical vacuum. I like to tell my friends that, you know, what particle physicists do most of their life is study nothing. Study the vacuum. In order to understand particles and their behavior, we have to first understand nothing, the vacuum. Now, the reason the vacuum is much more interesting than this picture is that in quantum mechanics, nothing can be this simple because of the uncertainty principle. Because let's say I really want to study the vacuum, then I probe it. I hit it with a photon, a quanta of light. I shine a flashlight on it, like this. And if I hit it, I disturb it. Now the vacuum is the arena, space-time, the arena in which the fields of electricity and magnetism, the electromagnetic fields and other fields live. And when I observe them, I give them a little kick. They fluctuate. Let me show you a picture, an illustration of what the vacuum really looks like. And I can do this because I'm a theorist, so I can calculate in a good theory what the vacuum really looks like, using QCD, of course. This is a picture of the quantum vacuum, which will be full of fluctuating fields. These are fields like the electromagnetic field, but these are the fields that transmit the strong nuclear force. And here it is. This is a calculation done using QCD, or theory of the strong interactions, put on a lattice, discretized, massive computer calculation of fluctuations in the fields that live in the vacuum on the scale of the nucleus. This is about the size of the proton, from here to here. You don't see that because you can't resolve distances that small, 10 to the minus 13 centimeters. But it's there. The vacuum is a very quantum chromodynamics that gives rise to the phenomena that we discovered that led to that theory. And you put them very close together, the force between them is very weak. And the closer they are together, the weaker the force is. That's the phenomena of asymptotic freedom. Which also explains why you can't take the quarks out of the proton, because when you pull them apart, the force gets stronger. And the quarks are confined, held together permanently inside the proton. That's confinement. Well, that was a very nice discovery, and it was only true in one kind of theory. So it led us to a theory later called quantum chromodynamics. It's a theory like electricity and magnetism, where the quarks have a charge. More charges than just one electric charge. There are 3 charges. And so the theory is richer, more complicated, more interesting. And by now it's understood that this theory really works with great precision and describes the nuclear force and the properties of the proton, the neutron, and all the particles you can create in energetic collisions between protons. We can now calculate the mass of the proton and the neutron and the other nuclear particles. What led to this? That's the King of Sweden. When you get a Nobel Prize, you get a check, which he's giving me here. You also get a certificate, which has a beautiful picture illustrated by a Swedish artist. And you see what he drew here was a proton with 3 quarks, which can't get out. In fact, they made a poster for the Nobel Prize that shows these 3 quarks trying to escape from the proton, but frustrated because the force is getting stronger and stronger and holding them back. It's a very pretty cartoon, but they got it wrong. Here they have these springs, these forces acting on a triangle like this. Here's a picture of what actually happens, according to the calculations, when you try to pull the quarks out of a proton. You see that you form the field lines form this triad, also preventing the quarks from getting out. This again is a massive computer calculation in QCD. With physics, let's turn to second area where we've made rapid advances, cosmology. There it is amazing how rapid things have changed. In 1 century, 100 years, we've learned that the universe is enormous, and our sun is only one of 100 billion stars in the Milky Way. But the Milky Way is not the universe. There are 100 billion galaxies in the universe. at the moment. And we learned that the universe is expanding like a balloon that you blow up, the surface of a balloon, expanding with almost a constant rate of expansion. And we learned that that expansion began about 13.7 billion years ago from some very hot state, which we call whimsically the Big Bang. We've expanded our horizons from the size, from the Earth to the solar system, to the galaxy, and to the universe, the visible universe as a whole, which is about 10 billion light years, the distance light travels in a year across. This is a picture of the universe as a whole, which shows very little structure. And we understand roughly, to a good extent, how this universe developed from a very, very small region of space. We understand most of the history of the universe. This is what it looked like. This is a picture of an almost uniform gas of light that when atoms, the universe expanded, it cooled, atoms formed out of electrons and nuclei. The atoms are neutral, the light streams through, and this is what we see 13.5 billion years later. That light hitting our eyes. And that light tells us that back then, the universe consisted of this gas of atoms and light, which was almost completely uniform. And the variations in color here, blown up by a factor of 10,000, show the little variations of density in that almost uniform ball of gas. But gravity attracts particles together, and regions that are more dense get pulled together. Regions that are less dense don't. Structure begins to form, and we now can follow that emergence of structure through the formation of stars to galaxies, planets, and we're about here. And most recently, we've learned that this sort of constant expansion of the size of the universe is actually accelerating due to something called dark energy. Light continue to accelerate forever. All of this history we've deduced from almost nothing, no understanding, in 100 years. That is fact. That and the question about what is going to happen in the future. Will the universe expand and indeed in an accelerated way forever? But most of the history, back to the first billion, from a billion, from a billion, from a billion, from a second, we understand. This is, in many ways, biology, which we're celebrating 150 years from last year of Darwin's publication of The Origin of Species. So over those 150 years, we have learned an incredible amount. We learned that life emerged over 3 billion years ago and was shaped by natural selection and random mutations. We have located and deciphered the genetic code, outlined the basic mechanism of living cells, and discovered the cause of disease. And finally, located the source of consciousness and emotion in the brain, and have started to explore its since the publication of the fundamental theory of life, namely natural selection, where it is Darwin hypothesized, it is now beyond doubt, that evolution via natural selection produces all the variations of living matter, starting with the origin of life, which largely is still mysterious, to Darwin himself. This has big implications for our consciousness as human beings. Using the genetic code as a marker, we can map out the human family tree and have now discovered that we all have a common ancestor and a common origin in Africa. I conclude with the prediction, the final prediction, that science will be even more important in tomorrow's world. It will continue to reveal more of nature's secrets, increase our control over its forces, with consequences that are both good and potentially bad. My hope is that the culture of science will inspire us to exploit the good and avoid the bad. Thank you.
Cosmology นะคะก็วานเนี่ยได้ถือกำเนิดมาจากปรากฏการณ์บิ๊กแบงเมื่อประมาณนะคะ 14,000 ล้านปีที่แล้วนะคะสำหรับทางด้านชีววิทยาซึ่งถือว่าเป็นวิทยาศาสตร์ที่ถือกำเนิดมาอย่าง
Your lecture is excellent. Listening to your excellent lecture aroused a lot of interest and questions. Can you take only 2 or 3 questions? I have a lot of questions. First one is a rumor that in year 2000, this is related to electromagnetism. In year 2012, there's a rumor that that would be the change of the field of magnetisms, the world magnetisms, and it will cause there were great destructions. There will be a great flood, great fire, volcano eruptions, whatever, and maybe a lot of millions of people will, somehow lost their lives. A lot of calamities to the world. That's a rumor. I'm a non-physics person. Question number. I'd like to hear your comments on this. And, let me finish with 2 other questions. Question number 2. Also, another rumor that running on the way of our Earth and will struck our Earth somehow. And a scientist, US I suppose, is creating a building and a rocket to shoot this far. It will be successful or not? Or we will hurt, struck our world, and a lot of people will lose their life. And the last one?
I'm scared to hear the last one.
The third question is, you mentioned that we should have overconsumptions and we avoid using fossil fuel to, especially cars in your country, in the US, that you consume so much energy, and other big countries. Can we avoid by using something alternative energy like hydro energy or hydrogen for water, and also well, dry cell like battery for car completely? Yeah, that's my question. I'd like to hear your comments and predictions about. Thank you.
2012. The only thing I know that happened in 2012 is when the Mayan calendar comes to the end of a cycle. So some people say that therefore there will be trouble. But even in Mayan, of course, you know, people don't do much about that, understand too much the Mayan astronomy or astrology. But I think the cycle just begins again and lasts for 10,000 years, like a very long time. So I don't think this. The meteorite, a comet, were hitting the Earth. We're in pretty good shape because we went for millions of years without knowing whether there was anything approaching the Earth. Now we can actually detect them and predict many years ahead of time whether they'll come close to the Earth. So I did read recently of some meteorites that will have a close encounter. That means 40,000 kilometers or more with the Earth, and that the probability of collisions is continually decreasing. But there are lots of people, both in Russia and the United States, who build rockets, who would love to have an excuse to build new rockets. But it's good to have the ability to see these things. I think the ability is good enough now so that if one saw a comet, or a comet is big, or a large meteorite, one would have enough time to maybe prepare a space vehicle that could change its course. As far as solving the energy problem goes, that's a long-term project. Eventually, it's probably solar power. Hydroelectric has been exploited everywhere in the world, almost to its full capacity. And wind is very useful where there is wind. But the sun is always there, and eventually, I think it'll be exploitable at a reasonable cost. The real problem is the next 50 years because we're so dependent on fossil fuels, not just oil, which we've been using up very rapidly, but coal, as you know. And as it turns out, the biggest coal reserves in the world happen to be in the US, China, India, and Russia, which also make the most pollution and CO2 emission. So where I hope a lot of attention should be invested is in figuring out how in an economically reasonable way to use that coal cleanly to remove the CO2 from the emissions. Otherwise, it's hard to imagine that the US, India, China will not use that coal. It's there, and it's cheap, and it's enormous amounts of it. It's very dangerous. So we have to pressure our governments and other governments to move towards clean use of fossil fuels that we will still use and developing renewable, clean energy sources. One of them is nuclear power. A part of the solution over the next few hundred years is nuclear power, which is clean. The only danger there is proliferation and the use. But that's a political problem and should be solved anyway. And nuclear energy is something I think should be, as China is doing, and the US is beginning to think about doing, and Europe is starting to do again. I nuclear power can be a very clean and economically viable way of producing energy. Well, a unified theory of all the forces is what I and many others have been working on for many, many years. And eventually we will find such a theory. It might not be a field theory, probably not, because one of the forces, the force of gravity, is very hard to understand in the framework of quantum field theory, which is the quantum theory we use to explain the nuclear forces and electromagnetism. That's why string theory is so exciting, because that's a framework in which gravity and the atomic and nuclear forces fit together very nicely. Such unified theories have other forces, if you want, or other phenomena that are not just explained by the standard model. And we expect any day to discover extra phenomena that are not explained by the standard model. We haven't directly seen it yet, but we expect it. I expect that at the LHC we will discover many new particles, new forces, if you want, that we haven't yet seen. But so on the one hand, we expect from the hints we have from nature that the forces we know and understand are all unified. But we also have a lot of new stuff we haven't yet seen. And if we saw, we would call new particles, new forces. But eventually, it's all just one thing. So both will, I think, we will understand better in the next decade. The new particles, the new forces, and more hints as to how they are all unified. Maybe in the string theory framework.
Ask a question to Professor Goss. It's not about particle physics, it's about global warming. And as I am teaching thermodynamics, and I would imagine that the Earth, and by absorbing radiation from the sun, we emit also some radiation from the Earth. But I do not believe that the rate of radiation in and out are equal. So there will be some trap into the Earth. And I have just my personal hypothesis that all the form of hydrocarbon element, the compounds, are actually a picky box for the entropy. And if we have another alternative energy from destroying or cutting down the chemical bonding between H and C, we will just release the devil to the Earth, and the Earth is actually full of to change the potential energy into the form of kinetic energy. And if you just cut down all this bonding, and you create entropy to the Earth, and if you cannot release this entropy out, the average temperature will increase, and this statistically will make more vibration into linear molecule, and you have new disease. That's just my story, but I don't know what about your opinion.
Well, on the Earth. So the Earth itself is heated. Most of the Earth is this massive core made out of iron and that is totally heated and regulated by radioactivity, by radioactive elements that are decaying. And the sun plays almost no role in the temperature of the Earth. We live on a teeny little infinitesimal layer of soil on the surface, and with a very teeny little atmosphere around us. That is a very precarious element on this massive planet. And that is affected almost entirely, although eruptions can change, that can affect that also on a geological timescale, by the sun. Now, the energy that comes from the sun is so much larger than all biological activity that until this growth of population and energy consumption continues for many, many thousand years, we're not going to drastically affect things the way you say, the way you were contemplating. What we're concerned about on this very delicate atmosphere is very small changes in the temperature, which are caused by basic physics of reflectivity and absorption of sunlight. Very small changes, like carbon dioxide, which is a greenhouse gas, or other greenhouse gases, can have a big effect on the temperature. But big for us is just a few degrees. This is the system of this atmospheric system is very unstable. It's very delicately balanced. We know historically has gone through large changes. What we don't know is what it will happen as a consequence of what we, for the first time, are doing over a very short time scale. And the biggest dangers are nonlinear effects. There are others which could drive us into a new region of equilibrium that is unknown to us. There are other planets nearby, like Venus or Mars, which would not be so pleasant for us to live on. We live in what is a narrow region of stability. And, but we're still far away from the region where the energy that we affect directly through industry or through biological activity competes with the sun, which is a steady source of energy, free energy.
Let me ask another question, if you allow. So,
until recently, neuroscientists rarely talked about consciousness because it was so impossible to imagine explaining consciousness. Now people are beginning to do that and probing the brain with new imaging techniques, new experimental techniques, new mapping techniques. I just received a few hours ago an email from a colleague of mine, a physicist who has become a neuroscientist, who is one of the pioneers of a new field called the connectome, like the genome, the connectome. This new field of mapping is intending to map the brain completely. It sounds totally crazy to me. They would like to map every connection between every neuron in your brain. There are 10 or 100 billion neurons in your brain, and each of them often has connections with another 1,000 neurons. So there's something like a 10 to the 11, 10 to the 14, which is 10 to the 14 is 1,000,000, 100 million connections. And presumably, each connection is complicated because there are different neurotransmitters in each connection. So you may be another factor of 10 to 100. You have 1,000 million code plan that would constitute the map of the human brain, much as the genetic code constitutes the map of the human genome. Now, if you had that, presumably the secret of consciousness would be somewhere there. And I believe that it probably is. And we will eventually make the connection. But we're not yet at the stage where I can even imagine what an explanation would look like.
We would have the metrics, I guess.
Sorry?
We would have the metrics.
So the goal of this project is to map out. Now this has been done with very simple organisms, some worms. Every neuron and every connection is all mapped out. Interestingly enough, even in those cases, the neuroscientists still can't exactly explain how those worms function, or whether they have a consciousness.
Thank you very much.
Yesterday we went to Ayutthaya.
As we always say, temples,
Ayutthaya.
Ayutthaya, which might be interesting or boring, I don't know.
Oh, it was fascinating. Very interesting. And and last time we did sightseeing in Bangkok, and the temples and the palace.
I think Ayutthaya also learned science from the West, especially from Europe.
Mm-hmm.
One of our kings also, the actual type, King Narai.
Right.
It's also sort of astronomist.
In Ayutthaya? Or
well,
in
King
Rama?
King Narai.
Narai.
King Narai is during the same period, but
Okay.
his other palace was in Lopburi,
Uh-huh.
which is not very far from Ayutthaya.
Mm-hmm.
And then that was like 400 plus years ago, so
Right.
Ayutthaya period. You saw what is left because of the
Invasion.
war, the invasion. And then in Ratanakosin era, like a couple hundred years ago,
Uh-huh.
King Rama,
The fifth,
the fourth,
fourth?
he predicted the eclipse.
Lunar eclipse.
Yeah, well, it remains a history of So first of all, how do you find Thailand? I mean, you have selected to come to Thailand in such a very important time of the year, you know, New Year celebration.
Right.
Is it worth it?
Well, it was very pleasant to celebrate New Year's here. It's beautiful surroundings, lovely hotel, and the people always seem to want to party, so it's a good place to celebrate New Year's.
Well, this is one of the, maybe the only Thai-owned international hotel chain.
Yes.
That's why the name is Dusit Thani.
Right.
Have you long been associated with Bridge project?
This is my second bridging tour. I came to Thailand in the Philippines 2 years ago, which was a wonderful experience, and so they invited me back this time to go to Thailand and Cambodia, which could use a bridge between them.
I have interviewed all the Nobel laureates who visited Thailand under this bridge project, the International Peace Foundation. I noticed that most of the invitation extended to scientists.
Well, most Nobel laureates are scientists. 3 out of 5 of the, well, I guess now there are 6. But, and if you count economics as a science, which I don't, then 4 out of 6 of the Nobel Prizes are in science.
Yeah, and that makes it difficult for me to ask good questions on science. But how life has been after 6 years, you know, you were awarded the Nobel Prize 6 years ago. How is your life
Busy.
outside science and physics? Is there any life outside science and physics?
Oh, sure. No, I mean, it's been very busy, and I've had opportunities to participate in other areas of that are outside my narrow scientific interests, such as this bridge program, for example, but also many other forums in which problems of the world, the climate, energy, and peace are being discussed. So it's been a very interesting 6 years. I've traveled a lot and met a lot of people, a lot of young people all over the world. Very interesting.
You've been recognized for your research in physics in the area, as I may quote the statement from the Nobel Foundation, you know, for the discovery of asymptotic freedom,
which nobody
in theory
understands.
of strong interaction.
Nobody understands. I mean, what I am a theorist. I work with pencil and paper, not in the laboratory. I just think and try to understand the basic laws of physics. So I work in an area which is about as far removed from applications as possible. And the work we did that led to the Nobel Prize was in trying to understand one of the 4 fundamental forces of nature. As you know, there are 4 forces in nature. There's gravity, and electromagnetism, electricity, and magnetism. And those were understood in the 17th and 19th centuries. And in the 20th century, we probed inside the atom and inside the nucleus at the center of the atom and understood how the atom works and eventually how the nucleus works. And inside the nucleus, where all your mass is located, the center of the atom, there are 2 new forces acting, and 2 new nuclear forces. One is called the weak force, and one is called the strong force. The strong force is what holds the nucleons together, what gives rise to the nucleons, the proton, the neutron, atomic energy, nuclear energy. And that's the force that I worked on and tried to understand what the proton, what are nuclei, what are you made out of? And in the end, we discovered a phenomena that led us to a theory this phenomena of asymptotic freedom, which allowed us to explain how protons could be made out of even smaller particles called quarks. You might have heard the name quarks.
Yeah.
And it turns out that all the nucleons, all the particles in the nucleus are made out of quarks, which are held together by a very strange force. And asymptotic freedom is that very strange feature of that force that led us to the theory. It's the feature that quarks, when they get close together, the force turns off. But when you try to pull them away, the force gets stronger. It's very much unlike other forces where when things get far apart, they don't have much force. No, they don't interact very strongly. With quarks, it's the opposite. Which is why, even though you're made out of quarks, no one has ever seen a quark. You can't pull them out of the proton. So we, from that, developed a theory which explains this nuclear force, and by now is very well tested and understood.
It seems like science, especially science in general and physics, your area in particular, has been evolving. I mean, there are different theories from the old time, gravity, relativity, Einstein, and then now I've heard of string theory, universe, multiverse. Right. It seems like you scientists have been looking for one and the same answer, who we are, where we come from, or what is the universe made of.
Well, there are questions that, children ask, and Homo sapiens have been asking for maybe...
An unsigned reporter asking.
And even ASEAN reporters asking. So many of those questions we've answered. Yeah. It's quite amazing. Many of the questions that I had 40 years ago when I started as a graduate student, like, what are the fundamental particles that make up all the matter around us? And how do they interact? And can we explain the laws of chemistry? Can we explain the materials in this room? By and large, we understand much of that. We asked questions where, how did the universe evolve? How did galaxies form? Why do stars shine? All of those questions we've more or less answered. We've asked questions like, what is life? Is there some new force? Or is it explainable just by chemistry and the behavior of atoms? And that we've answered. We don't know all the details. We certainly don't know the origin of life exactly, but we understand much of what life is in terms of atoms. So it's amazing, in a few hundred years, how much we've learned about the universe. We, for example, think we understand the history of the universe from right after the beginning, 13.5 billion years ago, till today. We understand how galaxies formed and how stars formed. But there are always more questions, and we continue to ask those questions. Like, how did the universe actually begin? And what are quarks made out of? Is there something more fundamental that unifies all these four forces into one force? And we think there is. And that's why we pursue these new directions like string theory or ideas relating to the origin of one universe or many. We're not sure. So the questions haven't stopped. We always can think of, as we learn more, we always seem to have new questions. And science goes on.
What if string theory is proved right? And what is going to happen to Einstein and
well, in physics, all theories are temporary, are provisional. But they don't disappear. Newton had a very good theory of mechanics and of gravity. And we now understand that Newton's theory is wrong. its basic concepts need serious revision with quantum mechanics, relativity, but still,
Is it totally wrong? Or
it's
just-
not, it's totally wrong in a sense. The assumptions that it makes and the basic conceptual framework is wrong. However, the theory itself is an extraordinarily good approximation to the better theory that came afterwards, quantum mechanics and relativity. When we send a rocket to the moon, we don't use quantum mechanics, we use Newtonian classical mechanics. We don't use Einstein's theory, even though it's the correct theory, because the velocities of the rockets are pretty slow compared to the velocity of light. And in that case, and the gravity is pretty weak, in that case, Newton's theory is a very good approximation. So even though theories at a fundamental level are wrong, like Newton's theory of mechanics and gravity, they are extremely good approximations in certain regimes to the newer theories. The theories we have today, which explain all of atomic physics, all of chemistry, in principle all of biology, based on quantum mechanics, electromagnetism, the nuclear forces, those theories are extraordinarily powerful, but yet we believe they're probably wrong in a deep sense. There's something that goes beyond them. But there's no doubt that when these newer theories are finally understood, the older theories will be very good approximations. If we want to understand the properties of atoms, we don't need any more than we have today, even though in some sense it's wrong. So science builds, successful science at the fundamental level builds on previous theories.
There have been so many theories to explain things in the world, but I've heard of the theory of everything. Is that the only one theory that scientists hope to get?
That's
to
the
explain
ultimate goal, the mecca, you know. And maybe there is. So the theory of everything refers to a fundamental theory that from which everything else could be deduced or understood in a very reductionist way. For example, we have a theory of everything that works at the atomic scale and bigger scales. We know how atoms work. We know the basic laws. I can write down on one T-shirt all the equations that in principle we need to understand the behavior of all the matter in this room, to explain all of chemistry and presumably all of biochemistry and biology. But most of science is engaged in working out the consequences of these basic principles, these equations. We can't solve the equations. We can test whether they work and whether they are at the origin, but to really understand how your brain works, for example, we're not going to sit down with these equations and try to solve them. We construct models based on chemical models or biochemical models. And science will always have a future in working out the consequences of the basic laws. But it could be that there, in the end, is one basic law, one set of principles, one theory of everything. But that would mean that, okay, we can stop looking for more basic particles or more basic laws, but it wouldn't stop us from trying to understand the structure of the world and the wonderful features of the world that are consequences, in principle, of those basic laws. And most of science is engaged in doing that. But this search for what are the basic constituents of matter, what is the force law that explains gravity and electromagnetism and the nuclear forces all as one entity, that's the goal of the final theory or the unified theory or the theory of everything. That was Einstein's dream, and we're still looking for.
New discoveries by science always have great impacts to the cultural thinking of humanity. This is, last year was the bicentennial celebration for Charles Darwin and 150-year celebration of publication of On the Origin of Species. Charles Darwin challenged the then existing religious belief.
Right.
It seems like great scientists and great discoveries challenge existing status quo of cultural belief. Do you think there will come a day when the relevance of the existence of God or the supernatural is no more because science had proved otherwise?
Well, it's retreated quite a bit from 10,000 years ago, or 1,000 years ago, or 500 years ago, or 100 years ago. The religious beliefs about nature have ceded much ground to science. For example, the origin of the how does life work, which used to be regarded as a different kind of force and energy and vitalism inside living creatures. We now understand that life is a very continuous thing from bacteria to humans. You know that you share 75% of your genome with yeast. Yeast and you are very similar. Scientists are looking at the genome of yeast to get genes that might be used to help humans conquer diseases. So you're not so different from yeast. That threatens, indeed, many religious beliefs in the very special nature of human beings compared to yeast or bacteria. I don't know how you can disprove the existence of God or prove it, but certainly some of the discoveries of science, the understanding, have eliminated or threatened superstition. Superstition is based on very simple explanations of how the world works. People always want to understand, and so they find an explanation that people like explanations, even if they're not correct. And science is a method that has allowed us to develop much better explanations, because we start from the assumption that we're probably wrong, and we have to continue to test our ideas and test them and throw them out if they don't work. Something I wish economists would do. When their ideas don't work and the economy collapses, they should throw out their ideas, old ideas. And the supernatural religious ideas don't subject themselves to this kind of testing all the time and throwing away ideas that don't work. So there could be threats to some of these old ideas in the future. For example, in physics now, in this basic science, in cosmology, we now believe we understand in great detail the history of the universe, almost to the beginning, the Big Bang. And in fact, one of the big areas of scientific research in my field, and in astronomy and astrophysics and cosmology, is to try to ask, the question we are asking is, how did the universe begin? And we don't even know how we would answer that question. But we might, in the end, be able to understand how the universe began and how it emerged the way it did. It's hard to imagine a good answer, but it was hard to imagine a good answer to the question, what is life? But now we understand that more or less. We're beginning to really understand what is life. So I actually think that we have a good chance of answering the question, how did the universe begin? And why does it look the way it does? And that could very well threaten various creation ideas that are based on religion or supernatural phenomena.
Developing countries usually are lagging behind in scientific progress, research, and science education. Looking at ASEAN, 10 ASEAN countries, what is your general perception of their science and development?
Well, so I've traveled much in Asia and Southeast Asia. The ASEAN countries in general are, well, there are exceptions, of course. Singapore is a major, becoming rapidly a major scientific player, even for a very small country. Certainly in applied sciences and technology, but in basic sciences as well. Singapore is determined to become a leader but outside of Singapore, the other countries of which I'm learning more definitely need to make further steps, if only to compete with their very close neighbors. Not compete. It's hard for a country like Thailand or even the ASEAN bloc as a whole to compete with China. But in order to have to be at the same level as China and not just a sort of lower level colony almost, or if you want to be on equal footing, you need to have the same level, I think, of education, science, and technology. And I think Singapore is an indication that there's nothing that's stopping you except the ambition and the desire to help. The children around the world are equally curious and fascinated and ambitious, and if they're given the opportunities with education, with the resources to take advantage of the opportunities around the world, and especially in today's age of communication and the internet, any country can rise rapidly and become a contributor to knowledge. I think every country should aspire to contribute to knowledge, because if you don't have people who are contributing to knowledge, the stage of the consequence of knowledge, technology, is going to always be a foreign product, and that's not good for a culture. It is certainly not good for the economy. So ASEAN countries have a way to go to catch up with countries which were much less developed than they, like China, Korea, but they should cooperate more. I mean, each country by itself is small, but by cooperating in these efforts.
Yeah, I think ASEAN does have this intra-regional cooperation in the area of science and other things.
It has it in principle. I don't know. I don't know how.
We just got the charter 1 year ago.
I don't know how effective it is.
But anyway, in Thailand, we seem to be doing quite a bit on our own in medical science and biotechnology. Yes. But overall, I think we are lagging behind in basic science education in school.
Yes.
What we should do? I mean.
Well, I mean, it's not easy to I mean, what my experience is that, and especially in Asian countries, is that children are fascinated by science. You must give them the opportunities to learn about it. You must have good teachers. The teachers must have the resources, must be supported. You must find ways of taking advantage of the communication system that is now available. You must give computers to the children. Teach them how to use the computer and access the whole world. I don't know how widespread computers are in classrooms around the country, but this is
Maybe in big cities.
But they can.
Well,
But
to
they're
know
much more important in rural areas, because there the teachers might not be so good. The opportunities, books are not available. But with a little $100 computer, which is hand powered and connected by two satellites, which are up there over all of Thailand, a kid can. So there are countries. See, I'm trying to remember Bolivia, I think, where the government has decided to give to every child at the age of 10 a computer, which is an investment. I mean, there are these small computers now which you can power by hand.
India also experimented.
And
with the
India is
whole
experimenting on that.
PDA handheld.
This will change the world, your world. Kids grow up very fast. If you give a kid education, it's an investment that immediately pays for itself in 5 years. And it's not very expensive compared to the reward you get. An investment of $200 a year for a kid who will, instead of having no skills, go on to college is an incredibly worthwhile investment.
Wouldn't you be worrying if they don't read books anymore? They don't read classic.
I think many of these kids have never seen a book or don't have libraries
Should they
available.
continue their reading habits of the classic literatures?
It changes. I read most of my books now on the Kindle.
Oh, yeah.
So they will read books over the internet, and they will be able to sit in their little village and download any book that was ever written. Google is going to put tens of millions of books available over Google. There is so much information that they can access this way. I wouldn't worry about it.
You are going to Chiang Mai University to give a special lecture. What are you looking forward to over there? What do you expect?
Well, I've given some lectures in Thailand before, and what I'm looking forward to most is interacting a bit with the young people, the young students who are still excited. You can feel their excitement. That's one of the most pleasurable things about this kind of activity, is just having the chance to meet and talk to, answer questions from, try to inspire them, the young people, because they have energy. It's very important to do this because it recharges my own batteries.
I think it's good that the Bridge project invites you up country to see a different setting, instead
Yes,
of a
I've
big
heard a
university
lot
like
about northern Thailand. I've never been there. Mountains, as opposed to flat, and the people I gather are
The
quite
weather
different.
is a bit cool.
Weather, right, which would be welcome. No, I look forward to it very much, and I also look forward to going to Cambodia after this.
I see. Are you giving out lecture to a university?
Yes, similar.
Have you been to Cambodia before?
No, I've never
see,
been to
I
Cambodia.
see,
And
Are you here with the family?
I'm here with my wife.
So you must, be a tourist a bit.
We are. We're going to go to Angkor Wat.
I've been watching some of the programs on TV, side channels and things like that, and some of the former astronauts came to present the program, asking everyone that the Nobel Prize is the best. I mean, go for it. I mean, it's just like the ultimate achievement in life. To me, I think society recognized the Nobel Laureate as the best brains in the world, and not only that, I mean, you contribute to the world.
Well, you know, most of your life, Nobel Prizes are usually awarded late in one's life, luckily. So otherwise you wouldn't have time to do the science that leads to the Nobel Prize. But, you know, you don't, prizes are very nice. They recognize important stuff, but most of your life you don't think about getting the Nobel Prize. The real joy of science is not getting prizes, but doing science. And you know, science is a lot of fun. There aren't very many places left to explore, except in scientific laboratories.
To me, you know, as a journalist, of course, I'm not going to win the Nobel Prize or anything like that, but it is my ultimate happiness to interview a Nobel laureate. I mean, you are the best people in the world. I wish you all the success. If there is any more success that you want to achieve, thank you, sir.
Thank you. This was a pleasure.
All right, กี่นาที I will